The previous lesson looked at Newton's second law and Newton's theory of gravitation. Now we're going to study some other everyday forces and learn about how to combine different forces that are acting on an object. Some of the most common forces you encounter every day are called contact forces. These are what stop things from accelerating towards the center of the Earth. When I put a book on my desk, for example, it has that force due to gravity acting on it, but it's at rest relative to the table, so there must be an exactly opposite force pushing up on the book. This is the contact force, and it is caused by interactions between the atoms in the book and the atoms in the desk. These interactions between the atoms are difficult to specify exactly, but we know that fundamentally they are due to electromagnetic forces, and we also know that the overall effect is to counteract the weight of the book exactly. If there were any extra force from the table pushing upwards on the book, it would accelerate up off the table. Now what happens if I tilt the table or put the book on a ramp? If the book stays at rest, then the contact force must still be acting to perfectly counteract the gravitational force. So now the contact force has a component acting away from the table and a component acting along the table. This outward force is called the normal force, and the force pushing along the table is friction. Notice that what I'm doing with these red and green vectors here is that I've set up an orthogonal coordinate system that matches the orientation of the table, rather than the orientation of gravitational force. And if we know the angle between the table and the gravitational force direction, we can use trigonometry to calculate the components of the contact force that are due to the normal force and the frictional force. The other point to notice is that we're working as if all the forces act at the center of mass of the book. This is enough information to track the motion of the center of mass of an object, but if we need to know how the object moves around its center of mass, we'll have to be a bit more careful. Let's go into a little bit more detail about frictional forces. In your own experience, you've probably observed that frictional forces vary with many factors, including the materials that are in contact, the roughness of the surfaces, temperature to some degree, and how fast the objects are moving relative to each other. For example, ice provides a lot less friction against the tires of a car than bitumen, and rough, raw timber provides more friction against your shoes than smooth, polished timber. And did you know aeroplane tires are heated before landing to increase the friction against the runway surface? Now, the force that acts when an object is sliding over another is called kinetic friction. In general, this is proportional to the normal force between the two objects. So that's another reason we like to write the contact force as two components, one normal and one tangential to the surface. The coefficient mu depends on the materials in contact, their roughness and temperature, but it doesn't vary strongly with the area of contact or the speed. A slightly different type of force acts when the two objects are at rest. This is called static friction. There will be a maximum value of static friction that can exist between two objects in contact, and this is larger than the kinetic frictional force experienced at a constant speed of sliding. You can test out a few of these assertions quite easily by placing a block on a ramp and changing the angle of the ramp. As you increase the slope, the normal force decreases, but the component of weight acting down the slope increases. Eventually, this component of weight reaches a maximum value of static friction and the block starts to slide. It accelerates down the slope, showing that kinetic friction is less than static friction. There is another type of frictional force when a solid moves through a fluid such as water or air. This type of friction is usually called drag. And the main difference between fluid friction and surface contact friction between solids is that drag strongly depends on the speed of the object relative to the fluid. Drag forces can also depend on the density of the fluid, its viscosity, and the shape of the solid object, by which I mean its cross-sectional area relative to the direction of motion. For small round particles moving slowly, drag is proportional to the speed. But for larger speeds and irregular objects, drag is proportional to the velocity squared. Now, it's drag forces that make it possible for skydivers to jump out of aeroplanes hundreds of meters above the ground. The skydiver accelerates until the drag force balances the gravitational force, and then he or she falls at the terminal velocity, a constant speed of around 200 kilometers per hour. Opening the parachute increases the cross-sectional area and the drag force, so the jumper decelerates until reaching a new terminal velocity that's safe to land. I think this is around 40 kilometers an hour. Other forces you encounter regularly every day are more direct manifestations of electromagnetic force, such as your fridge magnets, electric motors, or static electricity. For example, when your clothes stick together or attract your hair in really dry weather. A more detailed analysis of these forces will be covered in a different unit of study.